Hi everybody, my name is Amir. I'm a software engineer at Snyk, and I'm here to share a story about how we started building a new product from scratch and what a big role Redis played in this product building and how it helped us focus on what's important. So I'll start by giving a little bit of context about Snyk and what we do. We're an open source security company, which means we help our users, we encourage them to use open source, but we help them stay secure while doing it. We do this by scanning their project's manifest files. So for example, a project could be a GitHub repository, and a manifest file could be the requirements.txt for a Python project. It could be the package.json for a Node project, etc. We build a full dependencies graph of these dependencies because each of these dependencies have its own dependencies, and somewhere along the lines there could be security vulnerabilities. We match these dependencies against a security vulnerabilities database that we work very hard on building and maintaining. And then we can tell our users whether or not they are exposed to all sorts of exploitations. Moreover, we can help our users fix these issues by proposing all sorts of fixes. This is really good, but it doesn't always help. For example, if my runtime environment is different from the requirements that my GitHub repository offers. So we started working on a new runtime monitoring product, which was designed to help our users know what actually happens in their runtime environments. Because I would really like to know whether or not at runtime my product loads a vulnerable package, whether or not a vulnerable function is being called, which increases the risk of all sorts of security exploitations. So a few terms to begin with. Let's say a project could be a GitHub repository. A project could have multiple runtime instances. And each such instance should have some sort of running software that helps instrument and track what goes on there. And the vision is somehow presenting to our users whether or not, and as fast as we can, a vulnerability is being invoked. And the question is, how can we design such a system? So we started with a very naive implementation. We had these runtime agents for Java and Node. Agents are basically bits of software that run alongside the user's applications. And at some frequency, they send these bits of data containing information about what kind of exploitation and vulnerabilities are being invoked, if at all, at runtime. We called these bits of data beacons. And they're sent every minute or so to Snyk services. In Snyk, the microservice responsible for handling these beacons is called Homebase, and we needed to come up with a good and flexible way of storing all these beacons and aggregating them, while actually having no clear idea of what kind of data we want to store and how we would like to present it. We knew that eventually we'll have that idea, but we wanted to go to market as fast as we can and have some sort of basic idea of what's going on so we can tackle the problems that arise later on. So the naive implementation included a very basic instance of Redis. We didn't even care about persistency. Each project, which, as we said, could be a manifest file, got its own key in Redis. It was simply a list of items. Each such item is the beacon that an agent reports. So we're talking about a list of items. Each item contains information about the vulnerabilities invoked at runtime, if at all they exist. Storing a beacon is very simple because we use a list. So all we need to do then, when a beacon reaches our system, we just push it to the left of the list. We set an expiration time for the list because we want to make sure all the data we have is relevant and actual. And we trim any excess items because we don't want to expose ourselves to all sorts of denial of service attacks, to run out of memory, etc. Reading a project was also pretty simple. Given a project, we just needed to go to the relevant key that keeps all that project's beacons. We needed to retrieve them with LRange. We would parse them back into JavaScript objects. and then we would be able to serve all the relevant data whenever required. The cost for storing a beacon is pretty much constant because all we did was stringifying an object, push it to a list, and that's pretty much it. Reading a project is a bit more of a big deal because we need to read 1,000 objects and parse them back into JavaScript objects, which can take some kind of time. The great flexibility that we gained here was we had no idea what kind of data we're interested in, so we just kept it all, and later on we could extract whatever we wanted. Let's discuss the pros and cons of this first solution. So it took us very little time to implement it. We could focus on what makes sense for us and what's important for us to do. Expire and ltrim made sure that all the data we have is recent and makes sense for us. We had some sort of defensive mechanism against being spammed with beacons that if someone's trying to overload our services. Storing a beacon is very cheap, and since we had a flexible schema, we could change our minds at any minute and decide, okay, this part of the data is what I care about. The cons are that since we have the keys, our schema revolve around the project, then we can't differentiate between multiple instances of the same application. Moreover, the more agents report for the same project means that we have less data per agent. So we came up with the next solution. We decided that each such agent should roll up a unique identifier upon startup, and this would change our Redis schema. Instead of saving these beacons into one list per project, we would have a list per agent. Thus, we had multiple keys per project. It gave us a few advantages because it allows us to differentiate between different agents for the same application. So we could tell whether or not an application is being exploited at runtime through all its instances, only one instance. For example, if I had multiple environments, my production environment, my dev environment, we could differentiate between those. And all the data that we keep expires from whenever the key expires, meaning if an agent stopped reporting because, I don't know, an application instance went down, then all this data would be irrelevant whenever the expiry triggered. The cost for storing a beacon remained the same because we still just push one item into a list. But now reading a project starts being a bit more significant because first we needed to scan the Redis keys for anything that matches our beacon prefix for that project. So first we needed to scan all the relevant keys, after which has a linear cost for depending on how many keys are in Redis. Afterwards, when we had all these keys, we now needed to extract all these objects from these keys, parse them back into JavaScript objects, and only then we could extract the data that we're interested in. So we're talking about an increase of, by a factor of the number of agents that report for an application, meaning if my application has 5 runtime instances, then now the cost for understanding what happens to that application is multiplied by 5. Let's discuss the pros and cons. So expire and trim still make sure that our data is relevant. We are able to provide a greater value for our users because we can tell them how many instances they're running, where the vulnerabilities occur, etc. Storing a beacon is still very cheap, so we don't need to figure out what happens when we get too many beacons. And on the minus side, reading a project is starting to get slow. How slow, we didn't realize until a sunny day, or it was in December, so maybe it was raining, I don't know, and calls to Homebase, which are a microservice, started getting timeouts. We only know that requests take more than 2 seconds, but we didn't know why and how. So we started looking wherever we could. We started looking in our performance dashboards, but we didn't see anything meaningful. We clearly knew that the problem is reading a project, for example, not storing beacons. We checked New Relic, which helps break down how long each part of the application took. So it pointed towards both our middleware, which handles extracting the beacons, and towards the execution of LRange, claiming that each of them took about 2.5 seconds, which was pretty weird because we didn't expect LRange to take that long. And we also knew that Node's event loop is blocked, which gave us a great hint to understanding what's going on. We also noticed that we're handling way too many agents, which means keys, than we expected. Because, for example, even though my application has only 5 runtime instances, if I deploy 10 times a day, then suddenly I notice that I'm saving 10 times the keys. Trying to reproduce the problems offline in our local environments, we managed to view that actually what takes all this time is parsing all the objects from Redis back into JavaScript objects. Because parsing objects is both inefficient and blocking. Inefficient means it takes a lot of time to parse all these objects, and blocking means that since Node is single-threaded, whenever one request is getting served, all the other requests have to wait. So if I get 5 concurrent requests, and it takes me about 400 milliseconds to process just one request's worth of objects, then the last request would have to wait about 2 seconds before getting served. And 400 milliseconds was just for passing the objects. I'm excluding all scanning the keys, retrieving them from Redis, any other things we had to do about them. So it was time to find a better solution, which meant working a little bit harder whenever beacons arrive. We could now do that because running for a few weeks or months, we had some kind of idea what data we're interested in. So we knew how to extract from the beacons the bits of data that make sense for us and give value to our users. So we could break down a beacon for the vulnerable functions that were being called at runtime. And we decided to store them in a sorted set, which really complemented everything because we gave them a score based on the timestamp that they were seen, and Redis's mechanisms help us retrieve just the relevant data that we need because we could select them by the score. We kept the agent's heartbeats, which pretty much mean whether or not an agent is still alive in a list, but it didn't introduce any performance degradation because instead of saving this huge JSON object, all we needed to do is keep the timestamp there. We save all sorts of other bits of data, but it's not really interesting. And thanks to working slightly harder when beacons arrive, we could work significantly less hard whenever we needed to present a project's data to our users. So now reading a project is significantly faster. Each data type is pretty much optimized in its own data structure and makes sense for us to store it, and all data is still being discarded, so we won't get too much data in our Redis instance and nothing will get overflown. On the con side, we're now handling an elaborate schema for everything that we're saving, because instead of just having one prefix of beacons per project, we now have all sorts of keys for the vulnerable functions, for the heartbeats, for the loaded source. We also have a stricter API between reading and writing into Redis. If previously all we did was just throw objects into a list and then retrieving them, if we're not careful, then we could easily break. This is the last slide. So we've learned a lot about Redis. We've learned a lot about building a new project when you don't really know what you're trying to do. But Redis's flexibility helped us in focusing on what was important for us at that time. And whenever things started becoming more critical to handle, all the performance issues, only then we needed to focus on them. We made sure to monitor our applications so we know whenever we must handle all these performance issues. And before that, we could focus on what's important for us. And we could, since we did this in all sorts of iterations, we could keep giving our users greater value each time. That's it. Thank you very much for listening.